Hello. Do you have
Hello, how's it going?
Good. Do you have slides to share?
Sure.
Yeah. Cool. Yeah. So our next speaker is going to be Sean.
All right, thanks everyone for coming. Everyone hear me okay?
Yeah. Yep.
Fantastic. Okay, so it's the end of the day and I hear you guys are going to the pub soon, so we'll not spend too much time. But this talk is going to be on the operating system that we did called Xous, that is basically an embedded microkernel multiprocess thing. So the brief outline we're going to talk about is a little bit about me. I'm going to go over the project history, talk about why we built a new OS, what can it do, and more importantly, how can you actually use it? So to start with, I live in Singapore. I'm currently in Singapore, which is sad. It means I can't join you in the pub later. But I really like understanding systems. I work best when I understand them from the top to the bottom. And the lower level you go, the better. So kind of getting a holistic view of various systems. Now, about 10 years ago now, we did this project. It's the Novena Open Laptop. And we did it because we always wanted to have a custom laptop. This contained a relatively large Cortex A9 CPU with 32 gigabytes of SD and 4 gigabytes of RAM, and it ran Linux. And just to prove it literally was an open laptop, the whole hardware was public. But this thing ran a large Cortex A series processor with the full operating system. And Linux is large. There's millions of lines of code, and it's kind of difficult to keep the whole thing in your head all at once. The other end, the smaller end, we did this project called Chibitronics. We did Love to Code, which is a relatively small Cortex M0. It's 32K of flash, 4K of RAM. It was tiny. It ran Chibi OS. And the cool thing about this is that it's so small you could get the whole thing in your head at the same time. You could do so many cool things. We did a bit-banged USB stack for this. We were reading in audio frequency shift keying over sound to program this thing. It was pretty cool. So we have the large Novena, we have the small Chibitronics. Now we're working on this project called Precursor. Just kind of a block diagram on the left. And it's got two FPGA-based CPUs, RISC-V 32 IMAC, and it's got 128 megs of flash and 16 megs of RAM. And that's right smack in the middle of the two. Yeah. So the question is, what operating system do you put on this? Linux was large, ChibiOS was too small. Now, if you take a look at ARM's sales sheets, they have this concept called diverse embedded processing needs, where, and I'm pretty sure they did this just to be cute. They have the A, the R, and the M series. A being application, R being real time, and M being MCU. I don't know, they probably just needed something that started with M. But the A is pretty beefy. That's what is in your phone. That's what's in your desktop. If you have an ARM Cortex, it's got an MMU. That's the big thing that makes it special. M is small, has no MMU whatsoever. In the ARM architecture, they have 3 different levels, and the distinguishing characteristic is whether or not there's an MMU. And the whole point of this talk really is that MMUs are amazing, and I wish they were everywhere. You can get things like execute and place flash for free. If you have a tiny microcontroller, normally you have internal flash, but if you have an MMU, you could do crazy things like have an external device that runs off of SPI flash without having a special hardware block. ESP is very famous for doing this sort of thing. You could have swap space, you could have encrypted swap, you can have real-time support for patching broken hardware. So basically, when it came to operating system selection for Precursor, we knew that we wanted an MMU. We knew that it had to be RISC-V, and we knew that we didn't want Linux because it was a little bit too complicated for the kind of thing that we were working on. And there's this new thing called Rust, so maybe we can do that. So overall, the system design, The brief technical specs, the kernel itself is 17,000 lines of code. 7,000 of that is actually a RISC-V disassembler to work around a bug that's in GDB where it doesn't actually do single stepping if the target is a RISC-V or like a S360. It's got threads, it's got processes, so it's very similar to your desktop operating system in terms of what it does. But importantly, we've actually got tier 2 Rust support. So if you do Rust up target list, you'll actually see Xous as one of the targets in there. It's been built in since Rust 1.55, which just means that there's a target triple for it. Other specs, it is a microkernel, like I said, meaning it's very tiny, and everything is implemented in user space. So this is normal. Any program you have can request interrupts, and interrupts are actually handled in user space. All the drivers for things like serial ports, for tick timers, everything is in user space. And one special feature that we have is that each page of memory in the entire system that is legal can be mapped at most one time. So for example, when you have a driver, things like the serial port is actually a memory mapped IO. That driver can only be mapped to one process at a time. You can share memory from one process to another. You can lend it, just like you would lend memory in a function call in Rust. But every memory block can only be owned and accessed by at most one process at a given time. And because of microcontroller services, things like the consoles, things like the keyboard driver, all of these use well-defined API calls to communicate with different processes. One of the central tenets is that we only use stable Rust. So one of the things that I wanted to avoid from the very beginning is relying on nightly, because nightly tends to be unstable. So if you have a stable compiler, you can use Xous and build programs for it using just that stable compiler. I also wanted to make sure that no C compiler was required, because C toolchains are a mess. You have to get it for whichever platform you're using. It's different on Windows, Mac, and Linux. So the only thing you need a C compiler for, without any exception, is to build libstd. It's the standard library, because of things like libm has some C dependencies. But if you, as a user, were just going to build code for Xous, then you can do this without any sort of C compiler. I want to just mention that messages are everything in Xous. They form IPC. Message can be either a scalar, 1 to 5 scalars, like a U size, or it could be pages of memory, contiguous pages of memory. So when you pass a message from one process to another, you can either lend it or send it. So you can actually send memory from one process to another. And these calls could be either blocking, which means that your process, your thread, will sleep until that message is responded to, or non-blocking. And there are use cases for both of them. As an example, we use message IPC for sleeping. So there is a tick timer server, and you can call this function sleep with a number of milliseconds. And the process is basically these 4 steps. You connect to a server using a system call called tick timer, and then you send a message of a type blocking scalar. And one of the arguments to that is going to be the desired duration. And then what happens is the tick timer receives that, and the kernel will put that thread to sleep. And it'll just hang out there blocking until the tick timer server decides to respond. And so the way you implement sleep is you don't respond to that message until the tick timer expires. When the timer expires, it returns the scalar, and the existing program continues on. You can actually extend this a little bit longer, a little bit more complicated. You can get mutexes this way. So in your process, you have 2 threads. You can send messages from any thread. So the fast path in this case is just an atomic I size. And you increment it to lock it. You decrement it to unlock it. And we actually have this really cool thing where as long as only one thing accesses it at a time, you never actually need to involve a server at all. The tick timer server handles locking and unlocking, so the process is just sending messages back and forth, and from this you can build up mutexes, conditional variables, all sorts of complicated things that you need to build it in an operating system. And this is all handled in user space. None of this is really in the kernel. The only thing the kernel provides is interrupts and message passing and basic threads and processes. So, question, how can you use it? Well, I mentioned that MMUs are kind of difficult to find. Somebody did port this to an ARM, but it's somewhat rare. Unfortunately, the best place to use it is the precursor, which is somewhat difficult to get. Talk to vendors. Like if you have the ear of somebody, get them to put MMUs in your parts so you can do all these cool things. The easiest to use it is through Renode. You could see on the screen there's a picture of an emulator running it. We have the entire precursor emulated in Renode. But just get to know more about how all of this works. Get excited about putting MMUs in your embedded processes. Nobody does it, but I think that we really should be looking more into the cool things that you could do with an MMU in an embedded space. Thank you for listening. There's the URL of where it is if you want more information. And I guess, is there any questions?
I've got a question to start with. How does this sleep server sleep?
So the way it works is when there are no messages, it sits in a function call called receive message. And if there are no incoming messages, then that process is considered wait. And when there are no processes in the system that are actually running, when they're all waiting to receive either an interrupt or a message from another process, then the system can do a wait for interrupt or can otherwise gate the clocks and go into a low power mode.
Okay, and when it receives a message to like sort of to sleep, which then blocks until the time is over, how does it spend this time? Like normally you would implement that with a sleep, but how do you, if you are the function that is providing the sleep, how do you do that?
So in our implementation, the way it works is it has an array of the messages that need to be responded to, and there's an interrupt that fires. So you can actually access the array of messages that have yet to be written, yet to be responded to from an interrupt. And you can call certain system calls, such as a reply message, from an interrupt handler. And so what it does is it figures out what the next value of the monotonically increasing tick timer is, and it sets an interrupt to fire at that point. And when the interrupt fires, it responds to that. And until that's happening, it goes to sleep. Again, a process will be awoken if it receives a message or if it receives an interrupt.
So technically any program could implement its own sleep by doing the same interrupt stuff.
Yes, any program could implement its own sleep if it had access to the tick timer interrupt, because remember, everything can only be mapped once. So the tick timer is a block of memory. It's a register set. And the tick timer server, when it starts up, will take control of that block of memory, and it will take control of that interrupt. But if you're running on a chip that had two timers, then yes, you could have the tick timer take one of them and your process take the other, and they would run completely independently. But it's the sharing of memory, the sharing of these processes. The fact that you can't share memory is why you end up having to do this process. It helps synchronize all the different processes waiting for the same timer as well.
Cool. That makes sense. Thank you.
In the RISC-V privilege specification, there's, I think, an M mode, an S mode, and an A mode. I was just wondering, like, if this is targeting RISC-V, I'm just wondering, like, what is, I assume you're using that, like, what are you running things at? Is the kernel at M or S, and is the user space programs at A?
So, yeah, that's a good question. In RISC-V, the privilege spec, there is, as you say, there is M mode, machine mode, which is what the chip is when it first starts up. There's S mode, supervisor, and there's U mode, user mode, which is what it runs in normally. The kernel itself, process 1, runs in supervisor mode. and user space processes run in U mode. We never enter M mode once we enter the kernel. M mode is more for like, oh, I'm running on a chip that doesn't support atomic instructions, so I'm going to trap those and implement them in software. M mode for us is not very useful because it's missing the actual MMU isn't enabled, so memory translation isn't enabled at all. The big difference between supervisor mode that the kernel runs in and user mode that processes run in is supervisor mode has the ability to adjust, to modify the page table mappings of the process. So once you're in a user space process, you can't interfere with anybody else, but the kernel can change that mapping and do things like map memory and do switch between processes. So yes, the kernel runs at S. User space runs in U. Actually, one interesting thing is that even in supervisor mode, the kernel, each page of memory has a bit that says whether it's mapped accessible by supervisor or user space. So the kernel actually can't access user space memory. So if that happens, there's a violation and the system crashes. So we're protected both the user space process cannot modify the kernel, but also the kernel can't modify user space processes normally.
Thanks.
Did you consider using some of the other existing Rust embedded operating systems such as TOC or Hubris? I'm interested in what you found, whether they existed or if you found that they had things that you needed that they didn't provide for you.
So the only one I heard of, the only one I heard you mention was TOC. There was a couple of others as well. But it's strange. There really aren't many operating systems for ARM written in Rust. At least there weren't any that worked on stable Rust. I think TOC works on stable now. But first off, TOC didn't exist for RISC-V. We could have used TOC. But it also very much assumes that you're running on a Cortex-M. In fact, most of the operating systems are built on the assumption that you're running on a microcontroller that has no MMU. They rely on the ARM MPU if there's any memory protection at all. And we really wanted to have an MMU on the system just to ensure that if there was some sort of escape, that the process would at least be somewhat protected against the rogue process. It really was TOC that was really the only one available. There are a couple of others. I mean, we could have used Redox, I guess, but Redox is much, much too large for what we wanted. So there are a couple of others as well. There's one that's basically an interrupt vector handler, which maps really well onto Cortex-M's vectored interrupt approach. But for us, yeah, there just wasn't much out there at the time. And I'm still not sure that there is anything that fits this niche right in the middle of embedded microcontroller and full-on Linux / Redox I guess that would be it, Redox. What's next? So Renode is really the easiest way to get it working. Renode is a fantastic emulator. It's mostly written in C#, which is actually kind of nice because that means it works on Windows, Mac, Linux, and we have the peripherals written in C#, which means because it's an FPGA, Bunny, the FPGA designer, can change the hardware on a whim, and I can very easily implement software models for it. So Renode ended up being absolutely fantastic for testing it and doing rapid iteration. There's actually a chip that is being taped out right now, and we'll see how well that comes. It's called Cranium, and we'll see this new chip called Cranium should be able to run Xous. Bunny's been porting it. I mentioned earlier encrypted swap. Cranium actually has only 2 or 4 megabytes of memory on chip. So what they're going to do is they're going to do external RAM, SPI RAM. And it turns out that with the MMU, we can actually do encrypted swap and run the same programs. And we'll just swap out processes that are unused. And this is actually particularly nice for Rust when you have like format strings that are massive when it comes to these embedded systems. Most of that is probably not going to be used. The whole panic machinery isn't going to be used. So chances are that'll get paged out to the encrypted swap, and the system can run very comfortably in 2 to 4 megabytes of RAM. So hopefully that chip will be out soon. I think they're doing bring up right now. We'll see. If that works, then we'll have a very cheap source of microcontrollers. But for now, if you want to get involved, Renode is definitely the easiest way to do it, because you just download the software, run cargo xtask Renode image, and you can run it on your desktop and inspect what's going on, and get a full system running just very easily.
Cool. So that marks the end. Thank you everyone for coming.
All right.